This tutorial is all about constraints. Now, constraints can be said to define a physical transform or velocity relationship between two rigid bodies. So in this example, we have a car and we have a crane, and they're both rigid bodies, but also constraints that define the geometrical relationship between these rigid bodies. Now, we have ordinary constraints, and they usually remove one or more degrees of freedom between the two rigid bodies. So, for example, a prismatic removes 5 degrees of freedom and leaves 1, which is translation. We have hinge, which is a rotational joint. It removes 5 degrees of freedom and it leaves 1, which is a rotational axis. We have ball joint, which removes 3 degrees of freedom and leaves 3, the rotation between two rigid bodies. Now we have more constraints also that we'll bring up later. We also have something called secondary constraints, and those are constraints that operates on the remaining degree of freedom. For example, for a prismatic, we can have a motor, a lock, or a range, or a friction, and those secondary constraints operate on the free degree of freedom that is left between the two rigid bodies. So this motor can apply a force that moves these bodies relative to each other. Constraints can be created in many ways. We will see that when we get into AGX Unity. Now, just to have a look at the different equations that we need to solve here. We have the Newton's second law. And if we look at the constraint relationship here between Newton's law and the constraint formulation, we have what we call the state of a rigid body, which is the transformation and the velocities. So here we have F equals m times acceleration. We have the external force. We have the constraint reaction force, which is something that is computed by the solver. And of course, we have the mass times acceleration. So we have to make sure that this holds. If we look at the constraint formulation, we can see that we have a constraint reaction force. We have a violation, which is how far the two constraints have been torn apart. So the constraint is no longer non-violated. It has to apply some force or torque to restore its configuration. And this G here is something called Jacobian, which defines the geometric relationship. So we have some violation based on the position/orientation. We also have some violation related to the linear and angular velocity. But what's important here is that we have an epsilon here, and that is the compliance. It is defining the stiffness of the constraint. So we can have a really, really stiff constraint. Remember that for steel, we have a Young's modulus of 200 gigapascal. So it's very much related to the Young's modulus for contact materials, which we talked about previously. We also have something called damping, a damping time, which operates on the velocity. And this compliance and damping are very important parts of a constraint that we'll have a look at later. Now, just to be clear, the default value for this damping time should be 2 time steps. So in 50 Hertz, it should be 0.04 seconds. So let's go ahead and create some constraints in AGX Dynamics for Unity. First, we're going to create 2 rigid bodies here. We have one box, and then we'll just copy paste and make another box like this. So if we start simulation, we'll see that these two just fall in gravity. Now we would like to create a hinge that constrains the movement of this first rigid body here. We can see that we can create constraint in 2 different ways. One of them is to go up here in the menu and select whatever constraint I would like to create. Or I can use, if I have selected a rigid body, I can use this create new constraint tool. So let's click that and say, okay, we want to have a hinge. And next I have to define this, first of all, define what rigid body I would like to attach the constraint to, but also define the rotational axis. So in this case, we're going to use this position and rotation. And next we click this object here, and we get a hierarchy saying, okay, on the top we have the visual object, we have the box, and have the rigid body. It doesn't really matter which one you choose here. So in this case, I will just choose the rigid body. Now, what we can do is that we can use the tool, the constraint creation tool, to find a suitable edge. Because this is a primitive, we have a perfect center point, and this center point also defines some perfect axis. We can also find the edges of the visual mesh here, so we can use those for defining the edge. In this case, I would like to use this one here. And next we have to click, and we can see that we have sort of an indicator telling us that we need to define a point on this edge. And we have a snap functionality saying you want to be snapping over here at the corner or at the center. And in this case, we'll use the center point. Next, I actually define this rotation axis. So we can select any arrow that we would like that defines the axis that we want. So we'll click this one. So now we have the first definition of this constraint, but it's not created yet. We still have to click this create. And we just go ahead and click that. So now we actually have a constraint. So what happened then is that we have this rigid body, and we can see that it lists the constraints here that is attached to this rigid body. And here we have this hinge. If we now start the simulation, we will see that this rigid body, the bottom one, just falls down because it's not being constrained to anything. But this top box is actually constrained to the wall. And why is it constrained to the wall? Well, that's because it doesn't have any secondary connected frame here. So it's connected to null, or the world. Now, if we would like to create a second hinge that connects these two boxes together, we can do the same thing. We can select the new constraint tool. We click this one, select this visual object here, and we select anyone. We can select the box this time. It doesn't really matter because it will be attached to the same rigid body anyway. And then we select this edge here. We select a point, an axis, and next we're going to click on the other rigid body. So it doesn't really matter which one we choose here because they're all part of the same rigid body hierarchy. But we'll choose this rigid body here, and we click create. Don't forget that. Now we have two constraints, two hinges. So what happens then is that you actually have these two rigid bodies connected to each other. Now we can use this pull tool. So we click the button, keyboard button A, and use the left mouse to interact with these. Now notice that these two boxes, they go through each other. There's no collision detection being generated here. By default, collision is disabled between two constrained rigid bodies and their shapes. And this feature can be enabled or disabled by using this button. So let's have a look at the other properties of a constraint. The first one is translational properties. This is a hinge. That means that it has 5 degrees of freedom removed between the two rigid bodies, leaving just one, which is the rotational axis. So we have 3 degrees of freedom for translation that we can control using this hinge. And each of these degrees of freedom corresponds to one of the directions of this local axis of the hinge here. So if we would change this blue here, set it to something really, really high like this, it would mean that the stiffness in this direction would be very, very low. So if we would pick this, we'd see that it's actually behaving like a very soft spring in that direction. Remember that 1e or 2e minus 11, 200 gigapascal, or 1 over 200 gigapascal is the stiffness of steel. So that means that the default value here of 1 to the 10th of minus 8 is not steel, but it's still a very stiff value. And the fact that we can use this value to model our mechanical behavior is one of the strengths with AGX dynamics. We have a direct solver which allows for very high precision. So you can have a very stiff constraint or a soft constraint. That's completely up to the model that you would like to have. We can also specify the damping. By default, it should be 2 time steps in the time step that you're using. In this case, we're using 50 Hertz, so it should be 0.04. You can also use a damping to model a spring behavior. But remember, this is a damping time. It's not damping coefficient, which is something completely else. And I will recommend you to read in the AGX Dynamic User Manual, where there are examples how you can convert between the damping coefficient and the damping time that we're exposing here. You can also specify the maximum force in this case, because it's a translation. So you can specify that in Newton. So if you would like to have a constraint that can only carry 1000 Newton, you can actually specify that here. The second set of properties is for rotation, and it's very similar. The only difference is that this is a rotational degree of freedom, which means that, for example, this force range is in Newton meter and not in Newton. But otherwise, it's very similar. You can specify the stiffness for each degree of freedom, only 2, because the third one belongs to the rotational axis. Which brings us into the controllers. So let's remove this rigid body here and also this hinge. So we only have one hinge and one rigid body. We select the hinge and we open up the controllers. So here we can see the different controllers that we expose in AGX Dynamics for Unity. The first one we'll have a look at is target speed. If we enable that and give an initial speed of 1 radian per second, we start the simulation and we can see that the box actually rotates with a positive rotation around this constraint axis. If we set the speed to 0, it will get stationary. If we set the speed to negative, it will rotate in the other direction. We can also see that we can specify the compliance, or 1 over the stiffness of this constraint. And if we make it a really soft constraint, we can see that suddenly the motor is not stiff enough to actually succeed in overcoming the gravity. But if we make it stiffer, we can see that now suddenly it's stiff enough to apply a torque large enough to move around this body. We can also change the maximum available torque. We can see that it has 2 different values here. One is minus infinity and one is plus infinity. Now, right now the target speed is minus 1 radian per second. So if we change this to 0 torque available in this direction, it will not be strong enough to make this box rotate in the negative direction. However, if we change the target speed to 1, it will be strong enough to accelerate up to 1 meter per second. But we can see that it's not strong enough to actually deaccelerate to keep 1 meter per second, 1 radian per second. And that's because the force range for negative direction is 0. If we change this back to infinity, we can see that now it's able to rotate the box in 1 radian per second, or the whole 360 degrees. So we have control over how much we can accelerate in a certain direction or deaccelerate in the other direction. This parameter lock at 0 speed can be really useful sometimes. Now, a target speed controller is something that will try to keep the body at a certain speed around this rotational axis. It will, however, not guarantee that you keep a certain position. So if we would make this motor slightly less stiff and we start the simulation, we'll see that we'll reach a speed of 1 radian per second. But look what happened when I set the speed to 0. We can see that it just gradually drops in position. Now, this is also because I have used a compliance of 10 to the minus 5. But it's also the fact that this joint is made for keeping a certain speed. It doesn't guarantee that you will keep a certain position. If we want the motor to keep a certain position, we can use this lock at 0 speed. So whenever we set the speed to 0, we will actually transform this velocity constraint into a positional constraint, keeping the specific position, which is in most cases what you would like to do. You would like to control the speed, and then when you set it to 0, you want it to stand still, perfectly still. And if we would make this default stiffness again, we can start the motor, and then if we set the speed to 0, it will be perfectly still and it will hold this position forever, because now it's a positional constraint instead of a velocity constraint. So this can be very useful simulating cranes and things like that. Next, let's have a look at the range controller. So if we would start the motor with a target speed of 1, we can see that the box starts to rotate like this. If we change the direction to negative, it rotates in the other direction. Now, if we would like to limit the motion, we can use the range controller for this. So by default, it has a range of -infinity to +infinity, which means that there is basically no range. But we can set that to -2 and 2 radians. So if we now start the simulation, we still have the target speed of 1, but it will only reach 2 radians. And we can set the speed to negative and it will reach the negative range. We can also see that the compliance of a range is usually set to be stiffer than the motor. So we really want the range to behave like a mechanical stop. But at the same time, we can also use the force range to say the maximum torque that is available for this range to stop a motion. The third one is a lock controller. So let's disable the range and stop the simulation. The lock controller is actually operating on position. So if we disable the target speed and we start the simulation like this, we see that the box swings freely. But now if I would enable the lock, we can see that it actually moves the body to 0 position, and I can specify the target position where the rigid body should be in relation to this constraint configuration. So we can use this lock as a position controller, trying to reach a certain position. And at the same time here we have the compliance, so we can specify the stiffness, because all of these three work on the same degree of freedom and they can either cooperate or work against each other depending on the configuration. So we can use the lock to actually keep the constraint at a certain position. If we would increase the damping a lot here, let's set damping to 2 seconds, and I change the target position, we can see that suddenly it takes a long time before the constraint actually reaches. The two last controllers are electric motor and friction. So let's start the simulation, and here we have no controls available, so the box just swings freely. Now if we would enable the electric motor, but also enable the friction, we can set the friction to something fairly low like this, and then we enable the electric motor and we reduce the resistance in the armature. We can see that at some point we will get enough power from the electrical motor so that it can rotate this system. If we disable the motor, we can see that it quickly stops, and one of the reasons why it quickly stops is because of this friction. So this friction controllers is actually operating on this, once again, rotational axis of the hinge, and it will use the normal force that is orthogonal to this rotational axis. So the heavier this box, or the more force being applied to this box that is attached to its hinge, the higher the normal force will become, which will be multiplied with the friction coefficient here. So we can use this to actually model some rotational friction in this system. Otherwise, if we don't have any friction and we enable the motor, we will get a really, really high velocity because it will basically never stop accelerating. One thing that is very important to notice is that when you have a hinge or a rigid body rotating around a hinge in a very high speed, we can see that it becomes violated. And the reason for this is based on the numerical facts of sampling theory and the way that the constraints are being solved. We need to have a much, much higher sampling frequency to resolve a system like this. We usually recommend that you should have a time step that allows for 10 samples in a circle. So that if you have an object rotating faster so that we can't sample it 10 times during one lap, it will not be accurate to use for any sort of engineering measurements. Obviously, you can simulate things rotating faster like that, but you will then see a constraint that is being very violated in this axis. Also remember that setting the damping according to your time step. Let's have a look at the lock joint. A lock joint is a joint that will remove all 6 degrees freedom between two rigid bodies. So we're going to use this lock joint to simulate a beam of individual rigid bodies. So let's take the first lock joint and configure that. And we'll use the constraint tool to define the rotational axis and the attachment point. Then we copy all the lock joints that we need. And then we repeat this process for each of the lock joints so that we define this rotational axis, the attachment point, and also the secondary rigid body. For the first lock joint, we're going to do something special. We're going to attach the secondary one to none, which is the world. Let's have a look at the simulation we just built. So if we select one of the bodies, we can see that it has a mass of 1 ton. And they all have the same size and the same mass. So if we select all the joints here, let's first make these joints very, very stiff in all degrees of freedom. So we select a very small number here. And we can do that because of the direct solver, which allows us to have this kind of mathematical precision. And if we now simulate this, we can see that the beam is perfectly stiff. It doesn't flex at all in gravity. And if we try to manipulate it, nothing happens. It's very, very stiff. If we select one of the joints, we can see that we would like to set the stiffness around the rotation of this axis here. So select all the joints again, and we change the stiffness around this axis here, and we'll change it down to 10 to the minus 7. And now we can see that this beam flexes. So we can actually control the stiffness of this beam. We can make it mathematically perfectly stiff, and we can make it very, very, very flexible. And this is all because of the solver that we're using inside of AGX Dynamics for Unity. Now, as an exercise with constraints, we're going to try to build a small, simple car using hinge and something called cylindrical joint. So what we can see here is that we have one rigid body, which is the chassis, just a box, and we set the mass to 2 ton. And it has a box of a certain size. We also have something called steering, which is also a rigid body and it has some mass, 1 kilo here, and that's defined by this box here. Now, we don't want this box to collide with anything, so we disable the collision for that because it's not relevant. We only need the rigid body part. Next, what we're going to do is we're going to add a rigid body on this part here. So we select the wheel because this is purely a visual model. There is no rigid body information. So we just add a component rigid body. And then we can use this tool, create shape from child visual object. So we click that. We click the mesh that we would like to use as a blueprint for our shape. And then we can actually choose to use the cylinder as a shape. What happened then is that we have actually now created a shape, which is a cylinder. So if we select this shape that we just created, we can see that it's a cylinder, it has a certain radius, and it has a certain height, and it's actually matching the mesh model here. What we could also do is we could go to AGX Unity, create visual, and then we see that yes, this actually matches very well the original shape. But in theory, we don't need this visual part. So now we have a rigid body which has a shape, which is the cylinder. So now we want to create some constraints. And the first one we're going to create is a hinge. So we use this constraint tool. We select hinge. We choose this position and rotation, giving an axle. And we click this mesh here. And now we get the hierarchy of this game object. And what we're going to do, we're going to select this cylinder here. So we automatically get a very good rotational axis here. We can see that's the perfect axis, center axis of a cylinder. So we click that, and then we just select a point. It snaps into the center of the cylinder. Click that. We select the direction, and now we have created a hinge, or we have defined a hinge, an axis. Now we also need to select the other body, and we're going to use this box here. And we choose this steering rigid body. And then we click create. So what we have done now is creating a hinge between this tire and this steering rigid body. Now we need to attach this steering rigid body to the chassis. And we also have to do it in a way so we can steer this vehicle. And we're going to use something called a cylindrical joint. So we go here to the create constraint tool. Select cylindrical joint. We click this find position rotation given a principal edge, and then we click this rigid body here, select the rigid body, and we're going to choose this axis. It's going to be pretty well defined, going up and down. So we select this direction, we select the other body, which should be the chassis. So now what we have done is we've created a cylindrical joint going between this steering body and this chassis. Click create, and we have the constraint. Now if we start the simulation, it's not going to behave the way we want, because we can see that if I pick this, it just goes up and down, and it can turn like this. So there's a few things left. The first thing we should do is rename the constraints so we can find them easier afterwards. So we'll rename this to wheel cylindrical joint, and the second one to wheel hinge. So now we can easily identify which one is which. Then we go to the controllers, and we can see that we have a large set of controllers here. And the first part is for the linear part, going up and down, and the second part is the rotational, which is controlling the rotation around this vertical blue axis. So what we want to do, we want to use the linear part as the suspension. So we'll set some stiffness and some damping on that linear part. And then we're going to use the lock to actually control the rotation of this tire. So if we start simulation, we can see that we actually have some suspension going up and down. And if we select the wheel joint, we can control the rotation using the lock. We also might want to enable the range for the rotational motion. So if we select this cylindrical joint and we specify a rotational range of -0.2 and +0.2. And now if we start the simulation and we control the steering with the lock, we can see that it actually only goes between these -0.2 radians and +0.2. So now we have defined a good steering joint for this vehicle.